All right, thank you everyone and welcome. I'm Michael Bottom. I'm Miles's thesis advisor and this is his dissertation defense. Welcome especially to Miles's family who made the trip from the mainland and insisted on sitting in the back. For those of you who aren't aware of how this goes, first I'll give a brief introduction, then Miles will give his defense, which will last about 40-45 minutes. Afterwards, there'll be a period for anyone in the audience to ask questions. And following that, we're going to go to a closed session where Miles and the committee members, pictured here, will stay and the rest of everyone has to leave. And assuming that goes well, that'll last probably 30 minutes, a little 45 minutes. After that, we'll have a little garden party in the back to celebrate the completion of the PhD. So there's an IfA tradition where the advisor sort of gives an introduction to the student. So I will proceed along these lines as well. Assuming this, okay, so Miles' sort of orbital trajectory looks like this. He was born in Denver and grew up in Eastern Iowa and then attended university in Iowa. And following that, he took a long sort of hyperbolic path towards the University of Hawaii. As you can see, he was kind of a cute kid when he was young. You can see there are a few photos, including one with his dad. And after that, things kind of changed. I think where in college, you can see he developed a taste for the finer things in life. This was at Iowa State. Nice suits and exciting fine wines and fine brews and the finest grocery stores known to man. But despite this this difficult environment, he with many distractions, he actually did quite well at Iowa State. He was one of the winners of the space grant there and graduated magna cum laude with a major and two minors. And then after that, he of course came here to Hawaii. Here's some pictures from Miles's life in Hawaii. You can see one of them is with his graduate cohort pictured there, and large fruits, other things of that sort. And he started in Manoa, but came here as one of our now pretty healthy sized graduate student class here. At Hawaii, Miles continued to distinguish himself academically. He was one of the 2022 ARCS scholars, which are sort of the top graduate students from all the divisions in the university. And even among this kind of elite crowd, he was one of the two picked to be ARCS Scholars of the Year. With Brian Yamasaki from the medical school. There's a picture of that there. I think oftentimes people like to talk about the students' research and stuff. I think I'll let Miles do that himself. That's kind of the point of the defense, you might say. But I will say a big part of it was on using the Subaru telescope and with the greater sort of Skexeo ecosystem, which involves many people from many institutions. And a big part of this was actually building an instrument for the 8-meter Subaru telescope, which now you can use, which is quite a remarkable, I would say, achievement for a graduate student. I think I've not heard of something like that very often. And there you can see at the top right a first light on one of the nights where the conditions were not terrible. And I won't show the pictures that Miles has taken using this instrument because I think that's kind of the fun of the talk, to see pictures of other star systems and disks and stuff. You don't want to give away the entire thing. But I will say Miles actually takes other kinds of pictures as well, which some of you may know. He's actually quite a talented photographer. And I'll show a few of these here, just restricting to the ones from Hawaii. This one shows, if I'm not mistaken, this is after you get off the dirt path on the Mauna Kea road. Is that right? And then it starts getting paved. Yeah. So that shows that, and you can see the North Star, or right there, star trails. This is a picture of one of the Pu'us on Mauna Kea with the crescent moon. Quite a beautiful image, and it's it looks like there was maybe one car driving. It's a long exposure. And here's one of our auspicious comets that passed through in the last couple of years. And usually in the old days they would herald some great coming or going of something or other before we understood what they were. And this is my favorite. This is on the eruption from a few years ago, which it looks almost like Mordor or something. I don't really know. From Mauna Loa, you can see, and this was saying in the early morning, was it?
Yeah.
Yeah, I saw this one make the rounds on social media. Quite remarkable photo. You don't see that every day. Actually, since the family's here, you might actually see it. The eruption's been kind of nonstop in the last year or so. If you're staying for a few days. And also he hit what you might call the Nobel Prize of like people who take pictures of the sky, where one of his pictures was featured on Astronomy Picture of the Day, which is like, this is a big deal. Like before there was social media or anything, this is all people had, Astronomy Picture of the Day. And in high school, we'd all just talk about the astronomy picture of the day and all that, and what we saw like the day before or the week before. And so, this has been a very, very elite achievement in astrophotography. So I guess it's been, people like to sort of brag about their students' publications and stuff. And so I guess I'll do it. So Miles has about, let's see, 4 first author refereed papers. 1 is provisionally accepted, so I've listed that one at the top, and you'll hear about it in the talk. And then 2 very substantial, I would say, SPIE papers that he authored as well. And for people like us who do instrumentation, SPIE papers are like, they count. They're not like they're the real deal. But it's sort of, you can always count these things and do some kind of bean counting. I don't really particularly like to do that myself. But I would say he's a really good team player, and he's really helped a lot of people in many aspects and contributed to many papers, and just been generally a really positive force in my group. And I know many people listening online here are also, have worked with him, and he's just, really enabled a lot of great research. I don't think I've actually taught him anything in the last 2 years. I don't know. Don't answer that. But don't respond. But it seems like the knowledge transfer has been going the other way, which is, honestly what you want to see as an advisor. It's really, you kind of start to enjoy, your students' achievements, and you're happy when they finally surpass you. That's what you really want to see. So that's where we're at now. But just to underscore this point about, the other stuff he's been up to, like he's a really prolific in sort of the in the sort of greater astronomy like software package ecosystem, which are, and that just as a few, this isn't an exhaustive list of the sort of software that he's worked on. Many of these, by the way, have substantial user bases now. And many of them have been updated even in the last 2 months, which means you should have, did that really need to happen in the last 2 months?
That wasn't me. That's
Okay.
beautiful open source.
Okay, open source. Other people have done it. Good. All right. But Miles had started the ones in bold, which shows, some really substantial like ancillary benefits to the community. So I guess to finish, from this point forward, he's going to be taking a prize postdoc at Arizona in instrumentation and tech development, continuing his work sort of in the same sort of general area of high contrast imaging and polarimetry and adaptive optics. And I guess with that, I'll let you take it away. You'll probably need to connect here. But thank you all again for being here, and I'll turn it over to Miles.
Thanks for that introduction, Mike. Give me a moment to get my battle station ready. Yeah, I used to write a lot of code and then I got busy. Turns out dissertation is a lot of work. Okay.
confirm that people can see it and everything.
Yeah, is everything good on Zoom? Presumably. All right. Well, I've got a lot to say today, so I'm just gonna jump right in. Okay, so for an outline of the talk today, I'm gonna be giving you an introduction to exoplanet science and high contrast imaging. Then I'll discuss a search for exoplanets around nearby white dwarf Sirius B. Then I'll go into the upgrades I led for the Vampires instrument, followed by some early science. And finishing off, I'll show a dynamical analysis of a protoplanetary disk, and if we have time, some of my future research prospects. So in recent decades, exoplanet science has exploded as a field with almost 6,000 confirmed exoplanets to date. Profound questions like, are we alone and how did we get here, are closer than ever to being answered. Not only do exoplanets exist, they're quite ubiquitous. Exoplanets also show remarkable diversity, and if we compare what we've been able to see to the planets in our own solar system, they're actually quite different. This also highlights how we're not quite at the sensitivity levels to study the planets most similar to the ones in our own solar system. This also shows that the different detection methods kind of have their own parameter spaces, and they complement each other in terms of the exoplanets they can discover and the characteristics they probe. In today's talk, I'm going to be discussing direct imaging, which is this kind of minority in the top right. These are some of the most massive and youngest planets we've seen, as well as at the farthest separations. So very complementary to other work, but a bit of a minority. So what are direct images? Here are some examples. At their core, high contrast imaging is about taking photos of exoplanets. And from those photos, we can get their positions, which we can use to fit orbits and derive masses. And in addition, we get a measurement of their brightness as a function of wavelength, which lets us measure things like their temperature, radius, and the composition of the planets. This is especially important for searching for biosignatures and looking for habitable worlds. However, direct imaging is very challenging, and that's why there have been so few detections. The biggest obstacle is contrast, which is the ratio of the brightness from the planet to the star. Planets are relatively faint compared to stars. So for a Jupiter-like exoplanet around a sun-like star, you need 10 to the minus 9 contrast. And for an Earth-like exoplanet, it's even harder at 10 to the minus 10. For context, that's like trying to see a single bioluminescent algae cell right next to a lighthouse beacon. So very, very difficult. Planets are also very close to their stars, so the separation becomes a problem. Nearby stars are about 10 parsecs away, or 33 light years. And when you're that far away, the separation of planets like Earth or Jupiter become very, very small angles. So the angles we're looking at are 0.1 to 0.5 arc seconds. For context, the moon is half a degree. That's about half the width of your pinky at arm's length. And so the exoplanets we're looking for are about 1/40,000th the width of your pinky at arm's length. So extremely fine angles. Now, if we look at the contrast and separation here, this kind of defines our parameter space for direct imaging. And if we plot a lot of the currently detected exoplanets, they all fill in this lower left regime where they're very faint and very close to their stars. In the top right, however, show the detection limits for current generation high contrast instruments from both the ground and space. And you'll notice there's still a big gap in between these two parameter spaces. So that's part of the problem. However, there have been some detected exoplanets. So what are we looking for with direct imaging? Well, currently a lot of current instruments are not quite sensitive enough to reach that mature planet sensitivity. So instead, we're looking for hot, young planets. So right after planets form during their first few mega years of evolution, they're still incredibly hot just from the heat of them forming. And that heat turns into thermal emission, which makes the exoplanet much brighter by many orders of magnitude. So if Jupiter now is 10 to the minus 9 contrast, back when it was a baby planet, it was about 10 to the minus 6 contrast. So a lot of the detections that have been made have been very young, very massive giant planets. To take direct images requires a combination of large telescopes, diffraction control, sensitive detectors, adaptive optics, observational techniques, and extensive post-processing. So there's a lot of technology and instrumentation that goes into it. And to begin, I'm just going to spend a brief primer on image formation. So planets and stars are far enough away that they're effectively infinitely small when we look at them through the telescopes. However, due to the wave nature of light, there's diffraction, which means no matter how small that input image is, we get a finite response in the focal plane, which we call the point spread function here in the middle. The PSF is a function of the pupil geometry and size, as well as the wavelength we're observing at. So here I've simulated a 1 micron PSF through an 8-meter aperture. I'm showing the PSF here on a log scale, and this is our airy disk pattern. So it's got a bright central core, followed by concentric rings that fall off exponentially in brightness. This is in a log scale plot. It goes down to 10 to the minus 6. I've also plotted a scale bar with the separation of Jupiter at 10 parsecs, and we can see that we're not quite, at that 10 to the minus 9 level, even in a perfectly ideal scenario. So what I want you to take away from this is that diffraction is the ultimate limitation for high contrast imaging. Now, a couple more things to talk about diffraction. When we talk about telescope size, you want a large telescope because the smaller your telescope is, the larger your point spread function is going to be. When you have a larger point spread function, that means it's going to be brighter at the same separations, which means you have worse contrast sensitivity. So that's why we push towards large telescopes. Another thing that's important is wavelength. And instead of having the size of that telescope, if I double the wavelength of light we're observing, I also increase the size of the PSF. So we also want to push towards the smallest wavelengths that we can to get those nice small PSFs so that that radial fall off is maximized. So as I mentioned, even in a perfect scenario, diffraction is the ultimate limitation, but there's a class of optical techniques called coronography or diffraction control, which attenuates the on-axis stellar PSF while leaving the off-axis circumstellar signal from exoplanets and disks unperturbed. Here's an example of one of the first ever forms of diffraction control in here. The on-axis star is attenuated by a factor of 2 to 4 orders of magnitude, while the planet is completely unaffected. And so in combination, you reduce those contrast requirements in your images. Another thing that's very important for ground-based telescopes is atmospheric turbulence. So as light passes through Earth's atmosphere, this nice flat wavefront we get from the stars gets kind of corrupted by all of the turbulent eddies and the changes in refractive indices, and that kind of corrugates the wavefront and it's no longer planar. Here is an example of what turbulence looks like on Mauna Kea. This is a real example. The peak to valley here is about 8 micrometers. But what that means is that light going in on one side of your telescope versus the other have traveled different path lengths. And those variations in path length across the aperture of your telescope manifest as phase variations. So that's what you're seeing in the bottom left here. Those phase variations across the pupil create speckles. So they take that nice diffraction limited PSF here, and it spreads all that light all across our field of view. And you can see that the contrast of these speckles is much, much worse than this ideal PSF. So they're highly detrimental to high contrast imaging. If we can take, furthermore, all of these effects evolve pretty rapidly on the scale of milliseconds. So if you take really short exposures, you can kind of freeze the image and see the individual speckle field. But if you take longer exposures, they kind of blur out and form this fuzzy seeing limited halo. Finding an exoplanet with a PSF like this is pretty much impossible. The wavelength is an important term for calculating the actual phase variation. So you can see that optical path difference has an inverse relationship with the wavelength, which means that given the same optical path difference to the same atmosphere, depending on which wavelength you're observing at, you're going to get better or worse performance. So here with the same optical path difference, you get half as much phase variation at a longer wavelength. So again, the shorter wavelengths, while they have better angular resolution, it's much more difficult to contend with Earth's atmosphere. A critical component for a high contrast instrument is adaptive optics, which addresses these wavefront errors by measuring them in a control loop. So AO systems typically use deformable mirrors, which are mirror surfaces with little actuators that can change the surface, and that changed surface can perfectly correct the errors in the wavefront in theory. Here we can see how AO takes that seeing limited PSF and sharpens it back to a lot closer to that ideal PSF. So to review, high contrast imaging allows direct characterization of the position and the spectral distribution of exoplanets, but it's very technically challenging due to how faint and how relatively close planets are to their stars. Diffraction is the fundamental limit to high contrast imaging, requiring large telescopes, specialized optics, and additionally, atmospheric turbulence requires high performance adaptive optics to address. Now that we've covered some of the theory and instrumentation required for high contrast imaging, let's actually search for an exoplanet. In this case, we'll be searching for a planet around Sirius B, which is this little dot here. It's the brightest white dwarf. And it's next to the brightest star in the sky. So first off, why are we looking around planets around Sirius B or even white dwarfs in general? Well, for that contrast argument, instead of looking for planets that are brighter, what if we look at stars that are fainter? And that's exactly what white dwarfs are. As a normal star evolves and it ends up in this kind of late stage stellar remnant, it becomes a lot fainter. And what that does is it changes our contrast by a factor of maybe 10 to the 5, okay? So that makes it a lot easier to try and image mature giant planets. Additionally, it's very scientifically rich to study evolved stellar systems because we need to know more about how planets survive these post-main sequence evolutions. So as a quick primer for what happens to stars after their normal lifetime, intermediate mass stars become red giants after the main sequence. And when that happens, their photospheres puff up to hundreds of times their original radii. And when they puff up, any planets in their way are going to get engulfed and eaten up. So for the sun, it's in about 5 billion years, it's going to puff up to about 1.2 AU in radius, which means the Earth, unfortunately, will be consumed. But that's okay, 5 billion years, we got some time. Massive planets beyond that radius can still be heavily affected by tidal interactions, and the more massive the companion, the more it's affected. And so you can still get planets outside of the stellar radius that still get engulfed. And planets which survive this engulfment now live in a very different circumstellar environment with a lot more flux from that star because it's so much closer. Past the red giant phase, we move on to the asymptotic giant branch phase. And during this phase, we have a lot of mass loss due to stellar winds blowing the atmosphere away, and the star cannot keep them retained with gravity. When this happens, it loses mass, the star loses mass, which means it has less gravitational potential, which means any planets around it are going to expand their orbits. The combination of this orbital expansion and this engulfment radius kind of forms a forbidden zone close to the star where any companions there are not able to exist because they would not have survived this giant branch evolution. So the pathway for first generation or normal planets to survive is a bit uncertain and a bit chaotic. Now there are also theories for the existence of second generation planets which form during or after this giant branch evolution due to some exotic phenomena, all of which require a multi-star system. For example, you could get an accretion disk of material from the ejecta of one star, and in that accretion disk, perhaps you can form a planet. This can be extended even further, and you can get third generation or later generations in multi-star systems. Now moving on to, so our goal is to look at Sirius B to search for evidence of any forbidden planets or second generation planets. So now let's look at the Sirius system. It's one of the most well-studied binaries due to the brightness of Sirius A. We have really good estimates of the mass of both stars, as well as the white dwarf cooling age, so kind of how long Sirius B has been a white dwarf. All of these combine together to give us a really good estimate of the system age. And we can look back at our stellar evolution models and estimate that Sirius B started out as a relatively massive 5.5 solar mass star. And during its giant branch evolution, it's estimated to have expanded to about 5 AU in radius. So 5 AU we're going to mark as a kind of a critical radius for this engulfment zone. There isn't any prior evidence for exoplanets around Sirius B. There have been astrometric studies which look at the orbits of Sirius A and B, and if you see extra wobbles around Sirius B, that would imply some third companion, and that's been disproven down to 10 Jupiter mass. There's no evidence of any debris disk or pollution in the white dwarf itself. You can imagine if the dwarf swallowed up a planet, there might be some extra material at the surface. And there's also been imaging around Sirius B down to a couple Jupiter mass at 1 AU. Another important thing is there's been a dynamical analysis of the orbital space around Sirius B, and any orbits that are more than 1.5 AU away are not dynamically stable. So that means, in theory, if we find a companion around Sirius B, if it's actually captured around Sirius B, it has to be within this forbidden zone, because that 1.5 AU is much less than the 5 AU estimated radius during the giant evolution. We observed Sirius B 3 times in 2020 with Keck using NERC2 at L prime, so 3.8 micron. We use Sirius A as a guide star. So the faintness of white dwarfs is great for contrast, but it's bad for adaptive optics. Thankfully, Sirius A is a pretty bright star, so we had lots of photons to do AO with. We did not use a coronagraph, and that was due to these issues of diffraction. So again, Sirius A is the brightest star in the sky. Even when we're 11 arc seconds pointing away from it, we're still getting diffraction spikes from the PSF of that star. And this was sweeping through our field during the observations. Thankfully, it only overlapped with the image of Sirius B for a few frames, so we just kind of got rid of those. This data was processed using angular differential imaging. This exploits the rotation of the sky when using an Altaz telescope. So we use an image rotator, which stabilizes the telescope pupil, which keeps the PSF in the same orientation throughout the observation. That's what we're seeing here in this image. The PSF is in the same orientation, but the sky is appearing to rotate. This isn't orbital motion, it's just the sky rotating with respect to the telescope. From this, if we take this stack and you take a direct combination, a median combination, you get a sharp image of the PSF while the sky and the companions will blur out. However, if you then take that same data, rotate it to a common sky orientation, instead you're going to blur the PSF out and create a sharp image of the companion. So the key to ADI processing is generating a PSF model for each frame in the pupil stabilized data, and then subtracting it with minimal biases to the companion signal. So we then take these residual images, rotate them to the common sky frame, which is going to take all of those PSF residuals and blur them out, which allows the attenuation from this method, giving us 1 to 2 orders of magnitude better contrast. One of the first papers I wrote was a software paper, which does this kind of analysis using a variety of algorithms for doing that estimation of the PSF. So we used my package to test many different algorithms on our data and just choosing the best combination of algorithms and hyperparameters for each epoch. Here are the final reduced images. I've masked out the central full width half max of the PSF just because it's far too bright for us to see any planets there. There's unfortunately not any clear signals of planets in this data. Nonetheless, if you look at the quantitative statistical noise and look at the signal to noise maps and other metrics, there are no consistent significant detections in these data. Some of you may be thinking, what about those blobs really close in, but they don't really pass the smell test. If you just look at these two epochs and you ask, how massive would something have to be to orbit this much in 7 days? And it'd have to be about 0.6 solar mass, which is does not match well with the current astrometric limits around this star. If there was something that massive, it would be making the orbit of Sirius B wobble. So it's unlikely that these are any kind of real signal. It's much more likely that these are just residuals from that PSF subtraction process. Consistent with previous results, fortunately, we don't detect any exoplanets around Sirius B. But a non-detection is just an upper limit though, so we need to analyze our sensitivity, and we do this by calculating the noise in radial profiles, and we reach contrast down to about 10 to the minus 3, which doesn't sound like a lot, but it's significant for a giant planet around a white dwarf at these wavelengths. And we can take that contrast, and since we know the brightness of the star, we can say that if something was 1,000 times fainter than the star, then it would have this much brightness itself. And if we have a model for the planets and we know the brightness and we have an estimated age of the planets, we can convert that to a mass sensitivity limit, which is what we really want to care about. And there's 2 ages I want to test. So we have to kind of look at this first generation versus second generation problem. So if we have a first generation planet, which has somehow survived the giant branch evolution of Sirius B, it would be the system age at 226 megayear. So this is that red curve. However, if this is a second generation, if there were any second generation companions, they would have formed at the end of the giant branch evolution. And so instead we use the white dwarf cooling age, which is only 125 megayear. I mean, you can see how the younger age gives us a little bit better contrast here. So in total, from both of those results, we get anywhere from 0.6 Jupiter mass to 2 Jupiter mass sensitivity limits within this dynamically stable orbital regime. So in conclusion, we didn't detect any companions, but these are some of the deepest and most sensitive contrast limits, both around Sirius B and some of the most sensitive mass limits that have been done from the ground to date. And just to put this work in context, I know forbidden planet sounds a little crazy, but we've actually discovered an exoplanet within the forbidden region of a white dwarf. So there was a transit detection back in 2020. That was a Nature paper. And later on, this was confirmed with JWST. So there are exoplanets in the forbidden zone, and that's really intriguing. And there are other searches with JWST searching for white dwarfs. JWST is a great tool because it's really good at disentangling the really faint but mid-infrared, the thermal response between the white dwarf and the planet. Okay, so now let's move on to some of the instrumentation work I did leading the upgrades of vampires at Subaru. So why do we care about visible light, high contrast imaging? Well, the biggest thing is that we have this higher angular resolution, okay? So we have smaller point spread functions, which means we're going to get better contrast closer to the star. To highlight this, I'm showing here's an on-sky visible image of a really tight binary. It's about 70 milliarc seconds in separation. And here's what that same binary would look like at a much longer wavelength seen through a telescope like Keck. So the angular resolution gives you a lot better contrast sensitivity. Furthermore, there's lower thermal background, so the sky is a lot less bright at visible, and it's rarely the limiting factor in any observations. There's some nice bright emission lines, which are tracers of various astrophysical phenomena, specifically H-alpha, S2, and O3. In general, the technologies and the detectors and optics in visible light are a lot more mature and cheaper than those in the near infrared. However, by far, the biggest problem is that wavelength scaling of the atmosphere. So the shorter your wavelengths go, it's much more difficult to get a diffraction limited PSF, and you need orders of magnitude better adaptive optics to keep your PSF in check. Here's an on-sky visible PSF, which is a lot more erratic compared to that same longer wavelength PSF. One of the most important things for visible light high contrast imaging, though, is looking towards the future, towards detecting and characterizing Earth-like exoplanets around nearby stars. So for mature terrestrial exoplanets, they're not very hot, so they don't give off a lot of thermal emission. And it actually becomes easier to detect starlight, which reflects off the planets towards the observer. And this reflected spectrum is going to be most easily observed at visible wavelengths. In these reflected light spectrum, there are also many biosignatures. So this is really important for the search for habitable worlds, things like water, ozone, oxygen, methane, carbon dioxide, etc. However, with current generation telescopes and instruments, we're definitely not near these contrast levels, right? This is 10 to the minus 10 contrast. However, as we look towards the next generation of telescopes, 30-meter class and 6 to 8-meter class space telescopes, it's really important to keep developing these technologies and instrumentation so we can take advantage of those larger apertures when they're ready. And with that, I'll introduce vampires, the visible aperture masking polarimetric imager / interferometer for resolving exoplanet signatures, which is a visible light high contrast imager as part of the SKEX-AO instrument, the Subaru Chronographic Extreme Adaptive Optics platform on the 8.2 meter Subaru telescope here in Hawaii. Vampires operates at red wavelengths from 6 to 800 nanometers, and it benefits from two-stage cascading extreme AO to achieve diffraction limited imaging, even in the visible. Vampires is open to the community, so the public can propose to use it. Anyone in this room could, and it observes about 20 nights a year, give or take the semester. Here are some of the science cases for vampires. So with that high angular resolution, it's really well suited for stellar binaries that are really close. This is actually kind of a regime that's difficult to study with some other instruments. And with coronagraphy, we can also do low mass stellar companions down to the brown dwarf regime. And this, again, takes advantage of that two-stage extreme AO for good wavefront quality. With the polarimetry that Vampires has, it's also really well suited for circumstellar disk imaging. And furthermore, with that high angular resolution from the visible, it allows us to image even finer disk structures, so really high resolution images of disks. And thanks to the narrowband emission filters, specifically H-alpha, setting things like stellar atmospheres and jets, which we're seeing here, as well as emission nebula, as well, and accreting protoplanets, which is what we're seeing here. So these are some of the science cases for vampires. Here's an instrument schematic showing the light path. So light starts in the telescope, goes through some polarization optics. Then we have our first stage of extreme AO correction using a 3000 element deformable mirror. Then it goes through our second stage of extreme adaptive optics correction using a 2000 element deformable mirror. The visible light is reflected up through a periscope to a separate optical bench, which goes through some common path optics, and then into the kind of vampires regime here, where we have an alignment camera, some normal filters, some special filters, a beam splitter to send light to the two cameras we have, which also enables the polarimetry, and then another set of filters which can swap in front of each camera. Here's what that top optical bench looks like in CAD. So we're seeing that light path come in and going through all the same things. Just to give you context, this kind of this little box here where a lot of the fore optics for vampires are, and where there's a lot of things that I had to design and go and align at Summit. This is about this big, so it's very cramped and it's very difficult to do things like alignment. Making a post screw in is really hard because you can't fit your hand in to tighten the knob. So that's some of the difficulty. And here's what that same visible bench looks like in photos. So here on the left, these are the two cameras, the beam splitters, and some of those fore optics. The spacing between these dots is 1 inch, so that's for scale. And here on the right, it's a very cramped and busy instrument, but it can do a lot of things, and that's what's special about it. So I spent the majority of my dissertation working on upgrades to the Vampires instrument. Here are some of the comparisons between the old instrument and the new instrument. The catalyst for the upgrades were these two new detectors, which are have higher frame rates, better dynamic range, while being at least as sensitive as the previous ones. Vampires used to have no diffraction control, so one of the first things I did actually was develop coronagraphs for it, and some of the collaborators have developed some diffraction control optic as well. And there's also this multi-band imaging technique, which is kind of cool, and it gives us a lot of new opportunities with the instrument. So I'll begin talking about these CMOS detectors. So these are really low noise. And to highlight that here, as part of the characterization for these detectors, I took some histograms and analyzed their noise properties. And what's really special about these detectors is that the histogram shows that you can resolve individual photon events inside the detector, which in itself is pretty special just because that means it's really, really low noise. And this is without any kind of nuisance effects like electron multiplication, which can actually raise noise in certain aspects. Compared to the previous ENCCDs, if you look at this red curve versus the gray curves, we're just as higher is better. We're just as sensitive, if not more sensitive than the previous detectors, while again, having better frame rates, more dynamic range, and overall, they're just a lot more flexible. And over here, this is just, I also worked on a lot of the mechanical design and implementation, including ripping them apart and putting liquid cooling in them. I think our warranty's gone, but the liquid cooling hasn't leaked yet. I also worked on this multi-band imaging technique. This was a lot of fun. It's tough. This is only one slide. This was like over a year of work. But what this technique does is through these multiple short pass dichroics in a small angle of incidence, you can multiplex different filters into different fields on your detector plane. That multiplexing is enabled by these really precise spacers. So the spacers take each filter and they put it at a very specific angle, which determines where the image is located in the field. Having all of these reflections in this short stack is kind of problematic. It creates a lot of what we call ghost PSFs. And the way we solved that was by actually optimizing the geometry such that all of these kind of nuisance ghost PSFs end up outside of any of our main science fields of view. This has worked quite well on Sky. It's a really good in-between between just taking multiple pictures at different filters, switching a filter wheel at each one. Compared to that, we're getting about a 4x observing efficiency increase, but it also enables some new scientific opportunities as well as image processing opportunities by getting simultaneous measurements of the light at different wavelengths. Previously, vampires lacked any diffraction control, as I mentioned. So actually, one of the first things I did for the instrument was built 4 classic Leo coronagraphs. So here are some of the optics here. So these 4 tiny little squares with dots in them, I designed them. And I also designed this reflective mask here. So in combination, those form the coronagraph. And an image of that is shown here. I'll show some of the performance characteristics later. But I also want to show I worked with some collaborators on some other cool coronagraphs, including a vector vortex coronagraph and a shaped pupil mask, which is robust to low wind effects. I rewrote an entire control system for the instrument. It was all revolving around these camera viewers, which had keyboard shortcuts for doing a lot of the instrumentation. Feels a little bit like playing a video game. Also worked on a lot of asynchronous control and the asynchronous I/O. So this is really important because previously we were wasting time waiting for the data to write to disk, and now all of that data is asynchronous. So we kind of got almost a free 2x observing efficiency there. I also want to say everything's a lot easier to script now because it's all in Python, as long as command line interfaces. So if somebody wants to come in and write a script to do wavefront sensing and control with vampires, they totally can do it, and everything's already implemented with the real-time control system. I also developed an entire data processing pipeline for vampires. It helps address some of the instrument-specific problems while still being generic enough to handle almost every observing mode of the instrument. This is a lot, so I'm just gonna walk you through an example instead. So this is a multi-band imaging frame. So we have these 4 different images all on one detector frame. So I calibrate those detector frames and then I cut out each of those fields, align them all, and collapse them into these spectral cubes. From those spectral cubes, we analyze things like the flux, Strel ratio, and other important metrics. And additionally, the pipeline handles the polarimetry, including some of the instrument-specific calibrations that we've done. So this is what the pipeline can do. Here's some of the early science that we've done with vampires. This is a low mass stellar companion, HD 1160b, done with coronography. Here, the multiband imaging technique allows us to get the brightness of this low mass star as a function of wavelength, which is really useful for helping constraining the atmospheric models for these stars. This is kind of a nice, interesting field of research. And in addition here, we can see these are the contrast curves. So these are the sensitivity of the coronagraphs I built. And here we reach 10 to the minus 6 contrast at about 0.8 arc seconds or so, and 10 to the minus 4 at about 0.2, which I'm told is pretty good. In addition, with that multiband technique, what these black curves are showing you is that we can do some additional post-processing called spectral differential imaging, which lets us get even lower contrast. Here's a set of images from Neptune. The top row are the polarimetric images, actually, and you can see this characteristic limb brightening. This is exactly what we expect around a atmosphere like Neptune's. And on the bottom are the total intensity, and you can see some nice features here, especially in that third column. What the multiband technique allows here is you can get measurements of kind of the polarimetric response as a function of wavelength, which helps you study the scattering properties of the atmosphere of the planet. And here's a nice set of polarimetric images of the planet-forming disk, HD 169142, which I'm just going to use as a segue into the next section, because this whole paper was about that planet. I'm going to do a very quick primer over protoplanetary disks. The big question we need to answer is, how do planets form? We've discovered these thousands of exoplanet systems, but we don't yet have a clear mapping between kind of their initial protostellar conditions and the mature planets we've discovered today. And so we need to study planet formation as it's happening to answer these questions, and we do that by observing protoplanetary disks. Here are what the disks kind of look like as a schematic view. You have this large, inflated, and flared gas atmosphere, and this is best studied either through molecular emission lines like carbon monoxide, or through optical to near-infrared scattered light, where you get light from the star scattering off of submicron-sized grains. The other component of the disk, the larger solid bodies, the pebbles, the rocks, up to the kilometer-sized planetesimals that fall to the midplane. These are best probed by looking at their thermal emission in the radio and the millimeter regime. And so when you compare the radio millimeter regime to the scattered light regime, these are fundamentally probing different components of the disk, and we need to use all of these wavelengths to be able to form a holistic 3-dimensional view. In order to better understand the actual planet formation aspects, we need to study the local structures in disks. Some of those local structures can look like cavities, rings, arcs, gaps. For example, you can imagine as a planet forms, it's going to clear out the material around it, push it away, forming gaps. So we observe disks, look for these features, and try and understand if they're related to planet formation. But it's really important to understand the origin of the features, because there are non-planetary explanations for some things, such as photoevaporative or magnetohydrodynamic winds. Okay, now on to the HD 169142 system. It's a young star. It's a little bit more massive than the sun. It has this highly substructured disk. I'm going to walk through some of the features, starting with our millimeter emission, looking at the larger solid bodies. So there's a small little blip right around the star. That's probably an envelope of material directly on top of the star. Then a large inner cavity that's been cleared of gas and dust. And we have an inner ring of debris, another ring gap, and then a series of 3 rings and 2 gaps. It's a little bit easier to see in this schematic. And then when we look at the scattered light, which is probing that gas surface, what we see is somewhat similar morphology: an inner cavity, an inner ring, an annular ring gap, and then a diffuse outer ring. It's diffuse instead of seeing those kind of individually peaked structures. There are many hypotheses related to potential companions in this disk. One of them, which is exciting, is there's been a candidate protoplanet in this disk. There were some ADI observations from Sphere, and they saw this small little emission source. which moved between 2015 and 2019 with Keplerian velocity. This is at a separation of 37 AU, so it's in that big ring gap in the disk. There's also been some measurements using molecular emission line maps, which see that there is an excess of kinematic energy as well as some volatiles, all of which point towards the potential for a circumplanetary disk. So the disk that the planet is accreting mass and matter off of. If confirmed, that would be very exciting. This would be the second ever circumplanetary disk confirmed. There's also some evidence for a companion within the inner cavity. So here was a study that looked at variations in brightness in the inner ring itself and tracked these variations as they moved over time from different instruments. And they claimed that there was a shadow that moved faster than the rest of the disk, which could imply that there's something interior to the ring casting that shadow. And in this paper, they reported a candidate planet at 13 AU from the star casting a shadow. And this was the motivation for our study, since we figured, okay, we've got data back to 2012, and how fast does this move? About 5.2 degrees a year. Well, okay, we should be able to measure that, especially if we have data from the 2020s. So let's take a quick look at that math. The expected motion of anything within this disk is Keplerian motion, which is a function of just the stellar mass and the separation from the star. So for that inner ring, it's about 21 AU from the star, which means it moves about 5.2 degrees a year. And a fun little tool I'm going to use a couple times is you can derive an image transformation from this motion. So here I'm showing how I can take a single static image and kind of make it look like it goes back or forwards in time according to Keplerian motion. Okay, so let's look at all of the different data that has been taken on this disk. There's data going back to 2012 across a variety of instruments and wavelengths from visible to near infrared, both from SPHERE, GPI, and SkexAO. These first 6 are archival data sets I've received from collaborators or from archival websites, and the last 2 are new observations that were contributed for this work. Overall, they all show a similar morphology: inner cavity, inner ring, ring gap, outer ring. But now let's zoom into that inner ring. There's that report that studied these variations. Hopefully this shows a little bit better. There's some kind of brighter features and dimmer features. And a lot of these kind of bright and dim features actually exist in multiple epochs. Here it's a little easier to see in polar plots. So this is a clump, shadow, and another clump, another shadow, and kind of this outward bowing. And what I see in this data is that it appears like these features, not only do they exist in multiple epochs, but they appear like they're moving a little bit, like they're creeping up. So I'm going to use that image transformation I showed earlier for Keplerian motion to actually shear all of these images to a common time. So what this means is all of these data are in a common Keplerian reference frame, which means anything that aligns in this reference frame is moving with Keplerian motion. And what I see here is that those same features I was pointing out, these clumps and shadows, they look like they're lining up better in this common reference frame. So it looks like it's moving with Keplerian motion. However, it looks like something is not good enough for paper. We need to do a quantitative analysis. So I turn towards a technique called phase cross-correlation for actually analyzing and detecting the motion in this ring. Here's an example of how you can take 2 input signals, and through this technique, you get this response, which the location of this peak is exactly located at the value of the shift. I applied this to azimuthal profiles of the inner ring. So to show you what that kind of looks like, so you take you take any combination of 2 pairs of observations, you get their azimuthal profiles, you apply this cross correlation, and you get an offset just in terms of degrees of motion. And then I divide that by the time between observations to get the angular velocity between the epochs. So I did that for all 27 combinations of pairs of images I had, and then I averaged all of those together on a common grid to produce these 2 phase correlation curves, one for the inner ring and also one for the outer ring to study its motion. Now I found the peak of each of these correlation curves, which should give us the motion of the ring. And I've got that measured here in the table. And then I'm going to compare that to the expected Keplerian velocity. So here the inner ring is moving with about negative 5.1 degrees per year, which is almost exactly matched up to the Keplerian motion. So yes, the inner ring moves, and it's statistically significant, and it's best explained by Keplerian motion. So this already starts to rule out that shadow hypothesis. It doesn't look like any of these dimming or brightening features in the inner ring are moving at super or sub Keplerian velocities. Now, another hypothesis I wanted to study using the dynamics here is the theory of planet-induced spirals. So here on the left are hydrodynamic simulations showing how planets that are forming in a disk form spirals. And what's interesting is that these spirals move at the same velocity as the planet, which is different than the expected motion of just the disk. So the key here is that if you look at the location of the planet and just and calculate its expected velocity, which is about -2 degrees per year, if any of the features in the inner or outer ring were driven by this planet, they would have to have the same velocity. And not only does neither the inner nor outer ring match that velocity, the inner and outer ring would have to match each other if they were all driven by the same planet. So actually, if we look back at that discovery paper, they kind of pointed out that this might be an outer spiral wake, and I don't think it is, because this would have moved more if it was a spiral wake driven by this planet. There's another flavor of spirals that can occur that do move at Keplerian velocity, but the disk does not meet the criterion required for that. Furthermore, I don't really see any spirals in our data. If we had a Jupiter mass planet forming spirals, they would be pretty bright based on thermodynamic simulations, which have been done in the past decade, and they would be bright in both the dust emission and the scattered light. I just don't see it. So instead, I think it's more better explained that there's just clumps of material or changes in the composition or temperature around the disk. I just really want to point out the millimeter emission and the scattered light kind of fit together like puzzle pieces. Specifically, this little tendril here seems like it's carving out this feature almost. This tendril here seems like it's carving out this shadow feature. And right here, there's no millimeter emission, which is exactly where that outward bowing is. So it appears like there's some kind of interesting pressure trap happening here that's separating the smaller grains probed by the scatter light and the larger grains probed by the radio. Furthermore, they're all coincident with this H2O snowline region where you go from water ice to water vapor. So potentially some of these features are caused by differential dust evolution across the inner ring. So in conclusion, I've combined a bunch of polarimetric images from different high contrast images over a long baseline to study the dynamics of this disk. I analyzed the non-axisymmetric features and determined they move mostly with Keplerian velocity. I consider a few hypotheses for these features, things like spiral arms, which do not explain the motion, including spiral arms, shadows, as well as scattering effects or vortices. And looking towards the future, I think the most important thing to follow up for this study is to get more high-resolution millimeter data to see how that regime of the disk has evolved and if those features are long-lived. I don't have any time to discuss my future prospects, so we're going to see a lot of pretty pictures. I've done a lot of observations with SkexAO from visible to near-infrared simultaneously. This is a pretty cool disk. We see this feature in the visible that we don't see in the near-infrared. I was going to write a paper, got scooped, got more data, paper in the future. Here's another disk. This disk is special because you've got this little blob here, which is potentially a protoplanet. So there's a lot of interesting science here. And I think I have some of the highest angular resolution data of this disk to date. Paper coming up on that. This is not a disk or an exoplanet. This is a cataclysmic binary star, which is very exciting. This uses the H-alpha narrowband emission features of vampires. And there's some interesting astrophysics here happening with regard to the stellar jets that are coming from the accretion disk. So with that, I'd like to thank the many people who have supported, mentored, and inspired me throughout the course of my graduate studies. First and foremost, thank my advisor, Mike, whose guidance, patience, and trust have shaped not only this dissertation, but my growth as a scientist and how I approach research in the future. I really appreciate the independence I had to explore and learn, as well as the unwavering support for all the work throughout this journey. I'm especially grateful to the SkexAO team that I worked alongside during my dissertation. Olivier, Julian, Vincent, Sebastian, Kyohun, and everyone who's touched the instrument and made it what it is. This technical brilliance has been welcoming, and the collaborative spirit has made this work super enjoyable. It's been really intellectually rewarding and personally meaningful to be part of such a passionate group. And you've taught me all so much about optics, instrumentation, observing control systems, programming, system design, and what it means to contribute to a cutting-edge international collaboration. I want to especially thank the Vampires folks from Sydney, specifically Barnaby, who built Vampires the first time. Without his code to rewrite, this would have been a lot harder. So thanks to all of you. And thanks to all my colleagues and collaborators for the insightful discussion, shared challenges, and all the continued encouragement throughout this work. The community surrounding me has been one of the most energizing parts of this thesis. So To my friends and fellow graduate students, thank you for reminding me about the joys of life outside of research and being a source of laughter, perspective, and love through the most difficult moments. Finally, to my family, your constant love, support, and belief in me have meant everything. I would not be here without you, and I'm endlessly grateful to have you in my life. All right, thank you, everyone. I'm open to questions. I spent a lot of time making these accounts.
All right, thanks, Miles. So this is the part where maybe we'll start with people in the room, and then I noticed there's quite a few people online as well, and we'll maybe go to them second. So are there any questions from students in the room? Okay, any questions from non-students in the room? Not counting Olivier, who's on the committee. Okay, well, that's fine too. So let's see, Alexa, I see you have a raised hand. So can you try speaking and hopefully the sound will work? Are you muted maybe?
I think it kicked me out and then let me back in. Can you hear me all
I can hear
right?
you just fine.
Perfect. Thanks for the nice talk, Miles. I was wondering if you could go back to your case study of, what was that, HD 163296?
Yeah, this one.
Yeah, I was wondering basically if you could explain the outer disk motion, since that doesn't seem to be consistent with the Keplerian estimates that you had.
Yeah, so, well, let me show you, if we go back just so I can show you the features in this disk are quite diffuse. So in general, if you think about, like what is the location of this brightness feature, it covers a lot wider azimuth angles. So overall, the kind of precision of any method you would use for measuring its position is going to be a little bit low. So that's one reason kind of why we have this imprecision. Also, since it's further from the star, things are a little bit higher noise in general. And so that's just a little bit about why there's a little bit more imprecision. And then when you actually look at these, when you look at the error bars, they're relatively large. So here on this plot, actually, I have, this is the measured peak with error bars versus the expected Keplerian motion. So within, what's this? Within, 1 sigma, this is actually still explained by Keplerian motion. So we can't disregard the Keplerian motion as a hypothesis, but we also can't disregard the outer ring not moving at all as a hypothesis. Kind of the only conclusion I can make is that the outer ring is probably not being driven by the planet, since those are a little bit too high of a statistical difference. So there are other ways to kind of measure the motion in the disk that can give you higher precision. Things like fitting a Gaussian to a profile and seeing how that centroid moves. But I specifically chose this phase correlation technique to avoid making any model assumptions within the data, and just trying to use, all of the data together in a correlation way to measure the outer motion. So it's not as conclusive, but it doesn't really disprove anything except for that planet-driven effect.
Nice, thanks.
Okay, Max, go ahead.
Hey, very nice talk. I just had a question. Are these high contrast techniques or instruments like vampires, are these useful for any targets besides exoplanets? I don't know, either extragalactic things or other things within the Milky Way.
Yeah, so the difficulty, in theory, yes. In theory, you want to be able to take pictures of things like other galaxies with high resolution, right? Resolution is always good. Not only does it give you sharper features, it increases your sensitivity because you got more light and less space on your detectors. The biggest problem with some of these extragalactic observations are that when you look at an adaptive optics loop, one of the things, oh boy. None of you can see the adaptive optics loop now.
Yeah, I think you de-shared.
Yep. Okay, I won't do that in the future. I'll just say it. When in the adaptive optics loop, you need to measure the wavefront using some form of light coming into your instrument. And so if you're using the target you're studying as your light source for measuring the wavefront errors, which is usually a good choice, the problem is if the science target you're studying is too faint, since you're just making measurements of the wavefront by taking images fundamentally, if they're too faint, you actually get worse wavefront correction. So you actually have this whole kind of triangle of trade-offs where you want the AO loop to run really, really fast because the atmosphere is evolving fast. But then if you run it too fast, you don't have enough signal to noise in your wavefront sensing. And if you don't have enough signal to noise, you're going to have a noisier wavefront error measurement, which is just going to end up as noise in your correction. And so you can't win there. So that's kind of the big problem with a lot of these targets. They're just a bit too faint. One avenue pushing towards that is stuff called laser guide star adaptive optics, where you shoot a laser beam up into the atmosphere and you use that to measure the wavefront errors. And in certain cases, the laser can be a lot brighter than the stuff you're trying to study, and that works, but it has its own suite of complications, and it can only go so far because so far we can only make lasers that are so bright. I will point out there's been a lot of exciting studies about visible and near infrared wavelengths of some faint areas in the galactic center. So by being able to individually resolve these really, really fine sources of light that are in one of the most densest regions of our galaxy, the idea is that if you can resolve the individual stars and see how they're moving around the black hole at the center of our galaxy, then you can learn more about the mass of the black hole and some of its dynamic effects. So there are definitely use cases for it, but it starts pushing into a slightly different, technically difficult regime than what I've mentioned specifically for exoplanets and circumstellar disks.
I see. Excellent. Very well said. Nice talk again.
Thanks.
There is some solar system science you showed as well, and aren't some people proposing to do that as well?
Solar system science is also good. Things like asteroids, especially because small object on sky, high resolution, good. Again, they're faint. And another problem is that if you don't have an infinitely small point source, you actually get worse measurements and corrections of your wavefront. So those images of Neptune were actually pretty fuzzy relative to kind of the imaging quality we have for a lot of the stars, because Neptune is in a star, and so it's much more difficult to do adaptive optics using it as your wavefront guide star.
Okay, any other questions from either the audience here or online? Alan?
So thanks for the great talk. So as you mentioned, visible light was really hard, but the vampires image you showed looked very impressive. So I was just wondering, what is typically the image quality you get in vampires? Like how often do you get diffraction limited images and such?
Can you repeat the question too?
Yeah, so the overall question is, I've shown some images that show really good wavefront quality in the visible. So what kind of, how frequently does that happen? And I'm going to actually explain how we can address that a little bit. So first off, we have some of the, with vampires, we have one of the best AO systems on Earth. So that helps. A lot of money and technology and expertise that goes into making that work. Another thing that we can do is actually, I mentioned how if you take fast exposures, you can kind of freeze the speckle images. And that allows us to do this technique called lucky imaging, where even in imperfect conditions, if you can kind of freeze the speckles, what you can do is measure kind of how bad the PSF is and then just get rid of bad images. So here, that's what's showing going from left to right. This is discarding more and more data. This is essentially a trade-off between signal to noise and wavefront quality or angular resolution. And this is another really important technique to getting those high resolution images. So that's the majority of it. Really, really good AO and things like lucky imaging.
Okay, any last questions in the room or online? All right, going once, going twice, going 3 times. Okay, thanks again, Miles.